Here and there I've said, but this is really cool stuff. Quite honestly, what we're going to talk about today is the thing that got me into physics, or the thing that kept me in physics. This is the lesson that just blew my mind away. And for some of you, you won't have seen an ounce of it, and hopefully you will be blown away. For those of you who took general relativity, you've seen it. And this is where we're going to connect particle physics to general relativity in a very intimate way. But honestly, I'm glad you're all here because this is a pretty rad topic to talk about. And it's not going to be super detailed like Tuesday's discussion. This is going to be a little bit more idea heavy. We will have some math, but so what I've got written up here are my free Lagrangians for spin 0, spin 1/2, and spin 1 particles. And as we introduce them, what they talk about is basically the propagation of things, and there's momentum associated with these Lagrangians, and then the fact that if the field in question has mass, then there's an energetic contribution that comes from just having the excitation exist because it has mass. You've got to have the energy contribution from the mass of the object. So the first term on each of these is basically the derivative of the fields. The F mu nu is a little bit more complicated, but it's still just derivatives of the A field. So those are the kinetic terms, and then these are basically the mass energy terms. And what we're going to do today is we're going to add interactions to the story. We're going to ask, okay, how do these particles or how do these fields interact? Okay, so first of all, we should ask ourselves, what does a field interaction look like? Okay, you'll notice the Lagrangian for the scalar field just has the scalar phi in it. The Lagrangian for the spinor field just has psi. And so does the Lagrangian for the vector field just has A in it, even though F mu nu is built out of A. So if I wanted to have an interaction between, say, a scalar and a spinor field, what kind of term do you think needs to appear in the Lagrangian? Let me pick a card. Oh, look. Josh, it's going to get recycled to the bottom of the deck, but what kind of term do you think I would need to see in the Lagrangian to represent an interaction between a scalar and a spinor field? So I want a term that represents an interaction between a scalar and a spinor field. What do you think that term needs to look like?
That?
Yes, good, yeah. Maybe with some constant out front, but yeah, if I take a Lagrangian and I add a term which multiplies the two fields, this is an interaction of the fields. It says if you have a psi, then the presence of that psi influences the presence of phi. Okay? So I just want you to get an idea of what an interaction term might look like, because we're going to discover them later on through a symmetry argument. But I just want you to be prepared for, oh, that's an interaction term. Okay, so one might argue that you should take the Lagrangian for, say, a spinor field, because this is the matter field, and you should just add in as many interaction terms as you can think of, as long as the form of those terms are Lorentz invariant. Okay, we can't add in a term that's plus phi a mu, because that's not Lorentz invariant. So we could add in a term maybe like that, because this is a Lorentz scalar, right? But we could add in many, many terms like this. We could do a term like this. You could just keep making up more and more terms. Well, there's two interesting aspects of this story. Number one, today we're going to generate the terms that are really needed to give us the material to do calculations which agree with experiment. But then towards the end of the course, we're going to learn a lesson where, in reality, you do have to add all of these terms. Okay? but that's going to come a lot later. So the lesson today is going to be, we're going to explore a principle which tells us exactly what terms you should add for interactions. Okay, so there is an outline to this program, and I'll try and fit this in over here so I've got over there to work. And I got 4 simple steps. So first, we're going to begin with a free matter. And Madison, I know your card is on top, so you can go ahead and tell me if I'm going to be working with, starting with matter, Lagrangian, which of these 3 Lagrangians should I be starting with?
I don't remember.
Damn it. It was Sarah's card that was on top, and I called you Madison. I can't remember names anymore. So Sarah has to answer it because her card's on top. I'm not lying, so here's evidence.
Oh, you just pulled that from the middle.
No, I didn't. But I'll take answers from Sarah or Madison.
I don't know. So go.
Sarah, which of these Lagrangians, spin 0, spin a half, or spin 1, represents matter? What do I mean when I say the word matter? I mean the stuff we're made of. What are we made of?
Electrons and quarks.
We're made of quarks and electrons. Yeah, it's the spin a half. Okay. All right. So we want to start with a spin a half or a Dirac Lagrangian with some global symmetry. And I'm going to explore all of these in a concrete example. So we want to begin with a free matter Lagrangian and recognize or put onto it some global symmetry. Now remember, I used the words global and local before, and I will, through an example, give you explicitly what we mean by global and local. But the example that I gave you when I introduced these was if I took the particles and I did a global transformation, I just moved them all up here. But if I did a local transformation, I might move them in different places. This is not invariant under local transformations, but then if I take circles and I spin each of them about their axis, then I can do it globally or locally, and this is invariant under that transformation. Okay, so that's just a reminder of the difference between global and local, but we're of course not going to be using geometric transformations or symmetries, we're going to be using functional symmetries. So the second thing we want to do is we want to promote the global symmetry to a local one. Okay? Of course, we have to change the story, and this will be borne out in detail in the example, but you can't just take a theory with a global symmetry and say, I want to make it local, because usually it's not locally invariant. So we have to modify the theory a little bit to get it to be locally invariant. But one of the things we'll discover is that to make it locally invariant, you have to introduce a gauge field, which happens to be the thing that you find in the spin 1 Lagrangian. Okay? And this will induce interactions. So this is really the beautiful meat of this. It's by taking a global symmetry in an interaction-less theory, promoting it to a local symmetry, which forces us to introduce the interactions and tells us what form the interactions should take. It's a symmetry basis for forces. Okay? Now the third step is that we allow the gauge field to propagate. Because what the localization of the symmetry does is it introduces an interaction term, but because we have to introduce this A mu, and you get an interaction between the original fermion or the original spin half particle and the new spin 1 particle. But then this thing is just a background. You want to allow it to propagate. So what we do is we add in the Lagrangian kinetic term for a spin 1 particle. Okay, that way it can propagate. All right. And then step 4. You go have a beer. All right. Any questions? Well, I don't know.
Did you bring any to share with me?
But anyway, you're next on the list. All right, so what I'm going to do is I'm going to walk you through the most basic example of this with Lagrangians, okay? And it'll give us a lot of very important lessons, and then I'll tell you where we're going to go with it next. So here is our first example. So of course you know we're going to start with the spin a half particle Lagrangian. And it turns out that without actually doing anything to this Lagrangian, it already has a global symmetry. Okay? So first of all, remember that psi bar is defined as I psi dagger gamma 0. All right? And then the global symmetry that we're going to explore is psi goes to psi prime, which is going to be an exponential times psi, a complex exponential times psi, where q is a constant and phi is a constant. Right now it might seem a little excessive to write e to the I q phi, where q phi are two constants, but in a minute we're going to generalize this and you'll appreciate there being two things. But for now it just looks silly, okay? And then of course, this immediately tells us that the corresponding transformation to psi bar is that psi bar goes to psi bar prime, which is, and Sam is the lucky one who gets to tell me how psi bar transforms if psi transforms like this. Yeah. Okay. All right. Any questions? Okay, so let's just do a simple exercise. Let's check that our Lagrangian is in fact invariant under this set of transformations. Okay, this will go pretty quick. Psi bar, I get e to the minus iq phi, gamma mu d mu. And then psi, I transform with e to the I q phi times psi plus mc squared psi bar e to the minus iq phi. That's for the psi bar. Then the psi gets an e to the iq phi times psi. All right. We have two victims here. Dylan and Sophia. Sophia here?
Yeah.
Yeah, we are. Dylan and Sophia. And we'll go Dylan first. Dylan, you get the easier one. What's that equal to?
1.
Nice. Sweet. Sophia, can I move this thing past a derivative?
No.
Why not?
Oh, wait, it's constant.
Yes.
You can.
Yes. Yes. And this is just a number, so I can not only move it past the derivative, but I can move it past the gamma matrix. This is a matrix in spin space, but this is a number. You can always move a number past a matrix. So you can just bump this guy over here, and then what do these two combine to give you? 1, okay? Well, our Lagrangian transformed back into itself. Everybody on board? Yes. Is anybody missing what I'm saying? Okay. Now it's time to localize this. To localize this, what we're going to do is we're going to promote the transformation to the following form. Instead of e to the iq phi, we're going to have e to the iq phi, where phi is a function of where you are. Okay. So this is why I carried two parameters into the global example, because one of these is going to become a function, and the other one is still going to be a constant. Okay, we'll figure out the role that constant plays in a bit. All right. But does everybody understand that this is a local transformation? Right? Psi now goes to psi prime, which is e to the iq phi of x mu times psi. So I can change, or I'm multiplying psi by numbers which differ depending on where I am. That's the freedom of a local transformation. Okay, so let's see how this works out for the Lagrangian. And by the way, of course, the psi bar transforms in an analogous way to up here. Okay, nothing changes there. Okay, but now let's explore the Lagrangian. So the Lagrangian is going to be h bar c bar. We're going to put in the factor for psi bar. And the factor for psi. And then again, okay, let's pick two more victims. Nico and Ryan. Short. Nico, you get to go first. You're lucky. What is this?
1.
It's 1. Good. Ryan, you ready?
Uh-huh.
Can I move this past the derivative?
No,
Why?
because it depends on your position.
Yes, because the derivative is going to act on this. It's not a constant. So this is absolutely forbidden. Okay. I mean, you could take the derivative of this and do some junk, but the thing is, in order to have this thing be invariant, you need this to just show up over here and cancel, and that will not happen. Even if you take the derivative, it just won't happen. Okay? So this Lagrangian, while it is invariant under the global form of this transformation, it is not invariant under the local form. Okay? And now what we're going to do is we're going to change the Lagrangian to be invariant under the local form of this transformation. Okay? All right, so here is our approach. Yeah, I'll probably just rewrite some of this, but I'm going to need the space. So what we're going to do is we're going to replace the derivative operator, okay, with a new derivative operator, which we'll call capital D sub mu. And this new derivative operator is going to be the old derivative operator plus I times that constant q, which appeared in the transformations, times a mu. Yeah?
What motivates this choice?
When you ask me that, it's kind of interesting because the word motivation could mean what was the historical founding of how you make a global symmetry local. And that would have hung very dearly on how much math background the person had, because if a person knew about fiber bundles, then they would say, oh, I've got to break the tangent space to the fiber bundle into horizontal and vertical components, and therefore I need to introduce a connection, and I can pull that back to the base, and that corresponds to this A that I just introduced in the covariant derivative. That's a person with a fiber bundle background, but if you don't have a fiber bundle background, then you might just play around with it. And I don't know. The motivation, though, it's very, I mean, obviously what we're about to do is very similar to what we did in GR.
Yeah.
And I will give you the final lesson in terms of what we did in GR. But the basic idea is, no, I don't have a basic idea for you.
Yeah, so I'm gonna repeat my question in slightly different phrasing. So
Yeah.
back in GR, we had a motivation for introducing our new derivative in that our old derivative didn't transform right under.
Yeah. No, that's where that's where I'm gonna go with this.
Okay.
But the thing is, I could have motivated this that same way, right? I mean, but at the end of the day, yeah. And I'll make the connection. But at the end of the day, in GR, we were asking for the things to actually be tensorial. But things actually being tensorial actually corresponds to invariance of the Lagrangian underlying GR. We're doing an invariance of a Lagrangian argument. You could do the same thing to get the GR to get the modification of the GR derivative. We just weren't working with the Lagrangian in GR. We were just working with Einstein's equation. So that's why I didn't do that. But yeah, it's going to have the same argument that you want the derivative to basically be tensorial. It's going to work out exactly the same way. Exactly the same way.
So you were saying earlier that like introducing this stuff, like we're forced to introduce a mu and an interaction with like
Yes.
a one whatever. This seems like you just added a mu and it's going to work out fine.
Yes. Well, no. We've got to figure out some stuff about a mu
Okay.
before we can say it works out fine. So why don't you guys just sit back and let me go through this example and then save your questions for the end, because they might get resolved in the course of what I'm going to lay out. Okay? All right. So our new Lagrangian is exactly the same structure as this guy, except instead of partial mu, we're going to use this capital mu. And now what we want to do is we want to explore how this Lagrangian changes. Now, bear in mind that according to our transformation, which I erased conveniently, but I can write up again. Whoops, I need a sign there. Sidebar prime is sidebar prime e to the minus iq phi of x mu. Now, you might be wondering, hey, is this going to transform? And the answer is yes, this is going to transform, but right now we don't know how this transforms. We know how the matter field transforms. That was our beginning point. But how does this transform? We don't know. We will figure it out. Okay? We can't assume that it transforms the same way that the matter field does. In fact, it won't. Okay, so here we go. I'm just going to put these transformations into the Lagrangian. And I'm going to break up the d mu here into d mu plus iq a mu, because that's what we want to work with. Here we go. H bar c, psi bar. I get the transformation on psi bar. I get gamma mu, d mu, e to the iq, phi x mu, psi. So that's the d mu term. Now I'm going to move on to the iq a mu. So this is the term sitting in here, and I've got to transform a, but I don't know how to transform it, so I'm just going to leave it as a prime. Okay? And you might be bugged that I didn't transform this sidebar inside, but do I really need to do that? Do I need to worry about this term? No, because it'll just be 1. Okay? This is the term I need to worry about. This term is already invariant, even under the local transformation. Okay? So now, what I'm going to do is I'm going to take this derivative. And when I take the derivative, I'm not just going to get this term moving over for these to cancel. I'm going to create an extra term. But, this is the important observation, I haven't yet figured out how A transforms. So I might pick for A to transform in such a way that it cancels off the extra term that I gained by taking the derivative. Okay, so let me just do it. So h bar c psi bar e to the minus iq 5x mu. Oh yeah, I just want that working on that. Yeah. Everybody follow that? And I'm just going to take the derivative of the exponential here, and then in the second one I'm going to take the derivative of psi. It's just a product rule, that's all it is. This is one function, this is another function. Okay? Cleaning this up a bit. This derivative is in parentheses because the only thing the derivative is acting on is phi, which means that now I can pull the exponential over and yeah, go ahead, Allison.
Are you missing like e to the I terms in that second bit? Like where do those go?
In
'Cause
this bit?
Yeah.
Yeah, sorry. So this can be commuted with a mu prime and with gamma. There's no derivative here. The derivative is what I was having a hard time
Okay.
getting the e to the I to commute with. There's no derivative here, so I can move the e to the I over here and cancel it, just similarly to what happened the last term. Okay? Okay, so we can move this guy over here, cancel that, and all we're left with is that. And then combining these terms, we're going to have e to the I h bar c psi bar gamma mu d mu phi of x times psi. And these terms are the same. Okay? Maybe I'll just quickly write this out. For comparison, MC squared, no, sorry, IQ. Okay, let's pick a victim. Eric, you do this. I got faith in you. I want this thing to go back to that thing. Okay? This has got 3 terms. This has got 1, 2, 3, 4 terms. So what do I need to say that a mu prime is equal to so that this whole thing collapses back to that.
Del mu of psi x mu.
So notice this has got h bar c, psi bar, gamma mu, and a psi. This has got h bar c, gamma mu, psi bar, and a psi, and a gamma mu. So if I focus on it, hold on. So there's this, and there's this, and I want those to combine to become
Just
a mu.
so negative del mu sine x mu plus a mu. Yeah.
Does that look right? Everybody agree? So if a mu transforms like this, then this Lagrangian is invariant under this local transformation. Anybody ever seen this before? This is the gauge transformation in electromagnetism. It's written in a four-vector language, but if you broke it down into what it would look like if you worked in terms of three-dimensional space, it would be exactly the gauge transformation that you studied in that presumably you studied in electromagnetism.
I don't think we get into that until advanced, and like half the classes take that.
Okay.
Should we even call it a gauge transformation?
But forget about that for a minute. I want you to tell me what appeared. What is in our Lagrangian that is so incredibly special? Which term?
The second one.
Yeah, this term right here, which corresponds to these terms, this is an interaction. It's psi times a mu times psi with no derivatives. We did not set out to introduce an interaction. We set out to localize a symmetry. Localizing the symmetry required us to redefine the derivative with the introduction of the gauge field. But to make the Lagrangian invariant, this gauge field has to interact with the matter field that we started with. Okay? That is the backbone of the argument that an interaction can be governed by an underlying local symmetry. All right. Well, now let's move on to step 3 and allow the gauge field to propagate. Yeah, go ahead.
I'm sorry. What is a gauge field? Is it abstract or is it?
There are many different ways to answer this. We can say a gauge field is a field which has particles, so call it gauge particle or whatever, but it's a field which you must introduce to make the derivative well behaved under a local symmetry transformation. I mean, that's what a gauge field is. So a gauge field is always tied to a gauge symmetry. This is what we'll call a gauge symmetry henceforth. Okay? I mean, I could talk about horizontal and vertical decomposition of fiber bundle tangent spaces and so forth, and that would geometrize it for you, but we don't need to go there, trust me. But at this point, when I say gauge field, just think of a field that is intrinsically tied to a gauge symmetry, because it's the field you have to introduce so that the derivative is well behaved. And you'll get more comfortable with this because this is how we get all of the standard model forces. It's also how we get general relativity. It's how we get every force in nature. It's from localizing a symmetry and having to introduce a gauge field. The gauge field will play a special role when we do Feynman diagrams later because, for example, if we want to talk about the electromagnetic interaction between an electron and another electron, they exchange a gauge particle, which happens to be the photon. I'm throwing a lot of words at you. Some of them will sink in, some of them won't, but you'll work with this so much that it'll become more familiar. Okay? All right, so what we want to do now is we want to let this gauge field propagate, which means, of course, that we have to add in this guy. So let's do it. So if I add in a kinetic term for the gauge field, 1 over 16 pi f mu nu plus 1 over 8 pi mc over h bar squared a nu, then this is the term that describes the propagating A field. Because remember, A is also how we build F. Okay? A very important lesson to take from this. We would like to introduce the allowance of A to propagate, but we need to make sure that this thing is invariant under the local transformation. Okay? So let's check this out and see what happens. So if L1 goes to L1 prime, now we know how everything in here transforms because we know how A transforms, and A is the only thing that's in here. Okay, so we just need to transform A. So here we go. We got 1 over 16 pi, and I'm going to use the metric factors to bring these indices down so that this one is also built out of lower d mu A mu. But we've got d mu A mu prime minus d mu A mu prime, eta mu lambda eta mu rho times d lambda A prime rho minus d rho A lambda prime plus 1 over 8 pi mc over h bar squared A mu prime A mu prime. So all I've really done is I've replaced A everywhere it appears with an A prime, and I've made all the indices on all the fields lower. So I lowered this index down to an A mu and using the inverse metric, and then I did the same thing in the F's here because I have the transformation rule for A with a lower index. I just want to use a lower index on all my A's. Okay. So now all I do is I take this expression and I plug it in here for all the A primes. That's it. So if we do that, then we're going to have, and you know how this is going to go. And my phi's, when I write them, are functions of position. I'm not going to write that anymore because it's getting over. Okay, I literally just plugged in the expression for A mu prime, but giving it the appropriate index labeling based on where it was. Okay? Ready? Let's do it. Okay, so first of all, does this First line looked just like this. Yeah, I see Sam going, yeah, it does. Doesn't look like it to me. I mean, this is literally, this looks just like this without the primes. It's got 2 terms. These have 4. 4 times 4 is not 2 times 2. Well, let's hold on. This is d nu phi. This is d mu phi. Can we always swap d nu and d mu? Yes, you can. So I can swap d mu and d nu here, and then these terms cancel. Down here, I can swap the lambda rho. These terms cancel. And this line goes back to d mu a nu minus d nu a mu, which is f mu nu. D lambda rho minus d rho lambda, which is f rho lambda. Pretty impressive, huh? F mu nu is invariant under this local transformation. What about the mass term? I mean, it was always invariant here, right? Is this invariant? No. Sarah?
I don't know if this is important or not, but the first Lagrangian you wrote down, you have MC over like h bar squared and then quantity squared. Is that extra squared in the denominator not supposed to be there?
Oh, no, it's not. That's the thing. I wrote down MC over h bar and I meant to square the whole thing instead of just the denominator. Yeah.
Thank you.
Okay. But everybody look, the mass term is not invariant. So we're in a bit of a conundrum because we have to introduce the gauge field A in order for the matter Lagrangian to be invariant under this local symmetry transformation. Okay, we have to introduce A. You could introduce A and never let A propagate, but that's kind of weird because it just means our universe sits in a background of A that doesn't change. It's kind of weird. It's not very democratic in its degrees of freedom. So we want to let A propagate. But if we let A propagate with the Proco-Lagrangian, we screw up that local symmetry. Yes?
Can we just not have mass?
Yes. So what this is telling us is that A cannot have mass. And this is actually going to be the story for all of the forces. We'll find that no matter what symmetry I'm localizing, the gauge field I have to introduce to make that a symmetry is always going to be massless. Now that doesn't rock anybody's boat when they think about electromagnetism, because what's the mass of the photon? That's what this A mu corresponds to. What's the mass of the photon? 0. What about the gluons of QCD? You might not know, but they're massless. Okay? But what about the weak bosons?
Those have mass.
They have mass. So we run into this predicament where we want to use local symmetry to motivate the forces, but one of the forces in the standard model doesn't seem to work because it's got massive gauge bosons. And I'm saying boson, I'm adding the word boson because it's usually added, but these are bosons because they're spin 1. Okay? We will resolve that in a couple of weeks with the Higgs mechanism. Okay? So that'll be a huge motivation for the Higgs mechanism. But for now, I just want to finish up with some additional comments on this and making connections to what people seen in GR. But this is the story. You know, if you want to know what the Lagrangian should look like, you take this and you add this without that term. That's what your Lagrangian should look like. Sorry. This one. The one that's actually built with capital D. So if we take this guy, we add this Lagrangian with just 1/16 pi f mu nu, we're done. We have a action which is invariant under these transformations and this transformation, all at once. If I'm doing these transformations, I have to do these transformations and I have to do this transformation. These are all a single transformation. They just transform in different representations. This is what we often call the vector transformation because it's a matrix acting on an object. This is what we call the adjoint representation. Don't worry about that. It's just... Okay. So, what is the group that characterizes these transformations that I just did? What group do you think governs? I know you know, Ross. Sam? Yeah, this is U1. Okay? Remember, what is U1? U1 is a transformation which is complex. If you dagger it, which is complex conjugation transpose, this is just a number, so transpose it doesn't really mean anything, so this is equivalent to complex conjugation. Take a transformation, complex conjugate it, multiply it together, and you get 1. Well, that's what this is. Okay, that's obviously that lambda equals plus 1. So these are U1 transformations. All right? What theory is this? This is electromagnetism. Okay? I mean, you should have already seen hints of this because Maxwell's equations you get from this Lagrangian. Psi is what you would use to describe the electron field. So if you want to talk about how the electron field interacts via electromagnetism, this is the theory that you want to use. Okay? That also lets us kind of give an interpretation to this factor right here, Q. This is the interaction term, psi times A times psi. What do you think Q corresponds to? It's the charge. It is the strength of the electromagnetic interaction. In fact, you can write this down and then ask, what does this look like if I have a particle that has no interaction with the electromagnetic field? You just set Q to 0. Okay? All right, now, where is this going to go in the future? Well, what kind of symmetry is U1? What can you tell me about the group U1? Yeah, but it's only one term, so. Yeah, it's Abelian. Did Ross tell you it was Abelian?
No, I didn't.
He thought it into your head. Yeah, U1 is an Abelian group. That's part of the simplicity of this entire story because, as you might have learned from looking at some group stuff, once a group becomes non-Abelian, then you got to be careful about commuting things. Okay? Well, ask me, are we going to look at non-Abelian local symmetries?
Are we going to look into
Hell yes, we are. Definitely. Okay? Well, not today, but we'll turn into that next time. Okay? Because I've told you a gazillion times the standard model is based on not just the group U1, but also SU2 and SU3, which are non-Abelian groups. So the next time we meet, we'll play this story through for a non-Abelian group, and there'll be some differences. Okay. So I just want to make an observation which directly connects this to general relativity, and finish with one more observation out here. Oh, we're not. Okay, so there's a cleaner way to think about everything that I just did, which is kind of what Gabriel was suggesting. So it's good he left. Okay. I know. It's kind of weird. Okay. So here's what I'm going to say. Yeah, I'm gonna skip half of what's at the top of this, and you can look at it on the course map, and I'm just gonna write the final result. So what we discovered is that there is very different behavior if I take the partial derivative of a field, of a matter field, versus the, and this is what we call the covariant derivative. Okay, I'm sorry, I've got to throw some notation or some language out at you. So this is the covariant derivative. This is the one that's this plus the IQA mu term. Okay? But what we discover is that this thing transforms into that, which is not equal to e to the IQ phi x mu times d mu psi. Because I add this term right in front of the psi prime, and then I can't move it past the derivative. Okay? So this is not the way this operates. However, here, what I discover is that I have to transform not only psi, but I also have to transform d, because d has a in it. So d gets transformed. And if I do that, what I discover is that. So what we're doing is we're basically redefining the derivative so that when you transform the field the derivative is acting on and the derivative itself, the reflection of it is an overall factor times the original derivative of the field. And now you know this is multiplied by psi bar, and so the factor that transforms psi bar cancels with this, and that's where your invariance comes from. Yes?
This is kind of just random, but I'm having flashbacks. Was this one of our homework problems in GR to show this?
Yes.
Yeah. That was garbage.
So in GR, they were actually localizing a highly non-abelian symmetry, a very complicated space-time symmetry. But they were doing the same thing. They were basically redefining the derivative so that the derivative transformed with an overall factor. Of course, in that situation, it was identifying the derivative as a tensor. Okay?
Question too.
Yeah. Say it again?
There's a quiz question too, wasn't
Yeah. Okay? In GR, if you're curious, then the derivative in GR, and I'll write this just so that you don't think that I'm talking about this class. In GR, to get the covariant derivative, we take the original derivative and we have to add on this thing, but this time, this thing takes this field, or this Christoffel connection, is what we call it, actually carries 3 space-time indices. Okay, but don't worry about it. That's just a reflection of what we do in GR, and it is the realization that GR is just a gauge theory. I'm going to finish with one quick observation, which is going to play an important role when we're doing non-abelian gauge fields, but it's also going to directly connect back to what you guys did in GR. So you might wonder, where did this come from? And, for example, would I write the same thing if I'm doing a non-abelian field? Because, you know, things are going to transform more complicatedly, and maybe in the non-abelian case, things get more interesting. And it turns out that if you want to derive this from a starting point, then what you can do is you can take the commutator of 2 covariant derivatives acting on a field psi, and I've got the details worked out on the notes, but I'm just going to write the final result. It just ends up giving you IQ times F lower mu nu. So this means that we can actually redefine F mu nu. Instead of defining it this way, we can define it as minus I over Q times the commutator of the covariant derivative. Remember, you'll know what this covariant derivative is before you'll know what F mu nu is, because the covariant derivative you have to get if you just want the matter thing to be locally invariant. And then you're going to add on this thing. And I'm telling you, this is a more general way to write down what F mu nu should be. And it turns out that this generates different contributions when the group is non-abelian. But you should remember this from GR.
Something else? Something special, or?
Well, yeah, we call this the Riemann curvature tensor. Okay? But that doesn't matter, all right? All right, I'm done. I'm done, yeah. So next time you come in, we're going to take this to the non-abelian level. It will get more technically complicated, but the underlying theme is going to be exactly the same. We're going to start with a global symmetry, promote it to a local symmetry, and it will induce interactions, and we'll go from there.
It's fine, my parents are always meeting anyway. Oh my god.
That's actually writing out the law and
I know, that's why
Hey, Alex.
Yeah.
How many people in the entire world do you think understand fiber bundles as a formalism?
Oh yeah, turn it on.